Hello and welcome to this video about data structures. In this video, we'll learn how to test whether a matrix is a permutation matrix that permutes vectors that aren't in a standard basis. That is, a permutation matrix that is conjugated by a change of basis matrix. If you look here at the top, this can be represented by multiplying these vectors by this matrix until the same vector is encountered again. So we'll have a short sketchy proof that can make you understand that raising a permutation matrix to the power of a certain finite integer can make it equal to the identity matrix. So you'll agree that any permutation can be represented by this cyclic notation. This proof can work on any sort of permutation like this, with any number of cycles. When we square this permutation, then the inner cycle is eliminated, but we still have the two cycles at either end. And cubing this permutation would eliminate the first cycle containing 3 elements, and raising it to the power of 5 would eliminate the last cycle containing 5 elements. And so raising it to the power of 2 times 3 times 5 would eliminate all of the cycles, so the permutation would become the identity permutation. That is, a permutation that leaves any set of elements unchanged. And so we can say that we've successfully proven this theorem, although we'd need to generalize it more. So I'll just extend this proof to non-standard basis permutation matrices. We'll let P stand for a change of basis matrix. That's invertible. Any invertible matrix will do. And we'll conjugate M with P like this. We'll show that this matrix is equal to the identity when raised to the power of n, if the matrix M is. We'll just expand this expression out like this. Writing this bracket underneath this expression is a legitimate way of doing a math proof. And so, after manipulating this expression, we finally get the identity matrix, which proves this result for change of basis permutation matrices. The next step is to find the value of n. The number of permutations of length m is n factorial. So the number of times that we have to apply the permutation to itself to get the identity permutation is at most m factorial, because there are only this many possibilities, and if it is more than this, like m factorial plus 1, then a permutation must be found twice in this sequence, giving 2 different answers to being multiplied by m, giving a contradiction. But this is an extremely large number, and we can do better. And now we'll calculate this maximum value of k. So if the permutation has only one cycle of 2 elements, then k is 2 in this case. And similarly for 3 and 5. If a permutation has cycles of 2 and 3, then k is 6, because they are coprime, and k has to have both 2 and 3 as factors. If a permutation has cycles of 2 and 4, then k is 4, because applying the permutation 4 times would eliminate the cycle of 2 elements. If the permutation has 2 cycles of 2 elements, then k would be 2, because squaring the permutation would eliminate both cycles together. If the permutation has 3 cycles of 2, 3 and 6, then k would be 6, because applying the permutation 6 times would eliminate all the cycles together. So to find the smallest value of k, we'd need to create a computer program to find k according to these rules. So now to look at the strategy that we'll use for creating a table of values to look up the minimum integer to raise a matrix to the power of, so as to test to see if it's a permutation matrix. We'll firstly create a counter array, which consists of 1s and 0s in binary, and counts like a number in binary. Then we'll get a list of prime numbers and powers of prime numbers like 4, 8 and 9. Then for every combination of 1s and 0s in the counter, we'll get a list of cycles with different lengths. This list would contain the lengths of the cycles as integers and not as the cycles themselves. So if a cycle of 2 occurs with another power of 2 like 4 or 8, then we'll ignore this list of cycle lengths and go back to incrementing the counter. Like for example, in this case, we'll ignore this list and increment the counter. Then we'll get the sum and product of this list of cycles. Like for example, this is the product and sum of this list of cycles. We'll get the location of the table in which to insert the information. This location in the table is given by the smallest permutation that can contain these cycles, which is the sum of these cycles. And the product of these cycles is the power that we need to raise this permutation to so as to get the identity permutation, which is possibly the maximum value of k that we want to insert into this table. So to see if it is the maximum value, we'll take a look at what is in the table already and insert it into this table at this location if it's larger than what is already in there. Like for example, we'll look at the location of max p in this table at 21, which is the smallest possible permutation to contain all of these cycles. And if our product value of 231 is greater than what is already in there, then we'll insert this value into it. And then we'll do this for all of the values above 21, because these permutations can contain these cycles too. And we'll do this process for permutations of length 22, 23, 24, and so on. It's important to note that I didn't include any composites like this in the primes list that have 2 or more prime numbers as factors. If we did include 6, for example, then the maximum length of permutation necessary to contain it would be 6. But if we had cycles of length 2 and 3, this would have a maximum value of 6 to make it the identity, just like the cycle of 6. But it would only require a permutation of length 5 or more to contain it, so we can ignore the cycle of 6 for these purposes. But we will include powers of prime. I'm only including these powers for now. They are within range to give good values for numbers from 2 to 100. I should include all of the powers of primes like powers of 7 and 11, but these should work well for all of the numbers that we're working with now. So the form of the permutation requiring the greatest number of self-applications to become the identity is in this form, containing cycles that are all co-prime to each other, so that the product is a maximum. It may be that cycles of length 2 or 3 are left out, as long as all of the cycles are co-prime. Now to get the length of the counter, which is quite a bit complicated to calculate. Firstly, we'll get the sum of the consecutive prime numbers that's only just larger than n. For example, if n was 50, then these are the totals of the primes list that's only just below and above 50. We sum the numbers of these lists in order. Then we'll get the last prime in the second list that makes the sum only just larger than 50, and this is 17 in this case. And then we'll find its location in the list of primes and powers. And in this case it will be 11, because we want to have the option to include all of these numbers in any list of length of cycles. And these numbers should give the maximum amount of cycles for any of the permutations, and larger cycles than these won't be needed. Now to write some code to fill in a table of values for each maximum value of each value of k. We'll declare the function called getMaxPowers with all of its internal variables. I'll also include these lists of primes and powers of primes that I'll include at the beginning of the program file. We'll reset these indexing variables so as to calculate the size of the counter, that is, the maximum amount of cycles of different lengths that we can fit into a permutation of length n, which is the size of the table. We'll make up this loop to find the sum of the primes that's only just larger than n, which is the length of the permutation and amount of rows and columns of the matrix. We'll stop if we get to the end of the list before we finish, so I've put a -1 at the end of the list. I've also put a limit on the size of the indexing variable I, so as to avoid infinite loops. So if we're not at the end of the list, then we'll load in the next prime. So we'll add up each value in the list until we're bigger than n. And since this is a while loop, we'll increment the indexing variable at the bottom of this loop. Now we'll search for the location of this prime in the list of primes and powers, We'll firstly reset these variables. We'll make up this loop to go through the list of values. We'll get the location and value of the prime that we're looking for in the primes and powers list here. It should be in the list. If by some chance it isn't, then we'll locate the next biggest number that it found in this list. We'll increment this loop variable here while the prime number we're looking for hasn't been found in the list yet. So we'll set the length of the counter here. It should be equal to the location of this prime that we were searching for, and we'll increment it a bit. It should include all of the numbers that are necessary to find the largest value of k to raise the matrix to the power of that we're testing. We'll reset a table containing permutation lengths with its maximum integer that the matrix is to be raised to, so as to get the identity matrix. This is the maximum value of k in this table, and so there are n entries. I'll be setting n to be 100. We'll set all of the entries in this table to be 0 to start with, because we'll add entries to the table when the number is greater than the present entry. So 0 is a good value to start with. And we'll reset the counter, which contains the numbers of cycles of a certain value, like if we're analysing a permutation with cycles of 2, 3 and 5. Then we'll set all of these counter variables to be 1, 1, 0, 1 and 0 onwards. We'll reset this list of cycles. We don't really have to do this, but it is good to do it for debugging the code. We'll also get the number of times to increment the counter, which is given by this formula, because it is a binary counter. So this is the main loop where we'll count the array containing information on which cycles we have, and decide whether or not to place this information into the table. I've put in an extra variable called p to avoid infinite loops. This is where we'll increment the counter. The counter is an array of ones and zeros, and it behaves like a number in binary notation. We'll set this Boolean variable to be 1 to enter this loop. This loop also has a variable to avoid infinite loops. It can't pass 10,000. If the present counting variable is 1, we'll set it to 0 and decide to increment the next element in this array, which is what a counter does. And if the next element is 0, we'll make it a 1 and exit the counter. So now we'll convert the counter into a list of cycles. Each cycle appears only once in each list of cycles, and each location in the counter points to a number of cycles that this permutation can have in it. So we'll make up a loop to go through every element in the counter array. If the kth element in the counting array is a 1, then we'll include the corresponding cycle length in the list of cycles that we're making, and we'll increment the indexing variable to the list of cycles when a new cycle is included in this list. And finally, when we've finished constructing this list of cycles, then we can set the length of this list. We don't want any of these cycles to clash, so we'll reset these variables that count the number of cycles that are divisible by 2, 3 and 5. Like for example, 2 and 4 can't both be in the same list, because they are both divisible by 2. We should do this for all possible primes, but we'll just do these primes at the moment, because the lengths of the permutations aren't long enough for us to be too worried about them. We'll set this Boolean variable to false, so as to enter the loop. It says that we haven't found too many clashing cycles yet. We'll make up the loop to see if there aren't too many of these clashing cycles. This is where we'll count up the cycles that are divisible by 2, 3 or 5. We could generalize this loop for very large numbers and have a loop to go through 2 to 5, but we're working with smaller numbers now, but we could do this in future. We'll set this too many clashing cycles variable when we find 2 or more cycles that are divisible by these small primes. If we haven't found any clashing cycles, then we can start to evaluate this list of cycles. We'll reset these accumulated total variables. The total product variable is set to 1 because it is totaled by multiplication. This is where we evaluate these totals, which are the sums and products of these cycle lists. The total sum corresponds to where we must insert it into the table, so it can't be too large. We don't have that much control over it, so we'll just check that it isn't too large here. We'll have a look at what is in this location in this table already by setting this variable equal to it. So if the value found in this location is less than the value that we evaluated, then we'll insert this new value into the table at this location. The new value is the product of all the cycles in this list, which is equal to the maximum number to raise this permutation to the power of, so as to make it into the identity permutation. After this main loop, we'll make up a loop at the end of this function to go through every value in the table. And if the value of an element ahead of another element is less than it, then we'll set it to be equal to it, because a permutation that is longer can include all the cycles in a permutation that is shorter. Therefore, the maximum number of applications to return it to the identity must be greater than or equal to any permutation that is shorter than it. So this is an example of finding the maximum value of k for permutations of length 10. These are the cycle lengths for 10 that produce the maximum value. The maximum is given by the largest product, and these are the products. The first list produces a product of 30, so the maximum value would be 30 for 10. And here's the table that would be produced. The first column is the length of the permutation n. The second column is the maximum value required to make a permutation of length n into the identity. And the third column is the list of cycles corresponding to this maximum value. So now to write up a program that can test whether or not a matrix is a permutation matrix. We'll have to raise it to a certain power and test it continually. We'll declare the function with all of its variables. We'll get the maximum power that we have to raise it to from this table, which is quite fast once we have completed the table. The matrix must be a square matrix, otherwise we'll return false. And the matrix can't be too small. It must be a 2 by 2 or greater. You can't make a permutation from a 1 by 1 matrix. So we'll set the return boolean variable to be false and find an occasion for it to be true. It'll be true when one of its powers is the identity matrix. We'll keep multiplying this matrix by itself until it's the identity. We have to make another copy of this matrix for it to work. This is the loop where we increase the power of this matrix. We won't multiply it by itself more than n times, and n is set to a fairly low number, so the function won't take forever to run. This is why we created the table of maximum values, so as to find a minimum value of n so that this loop can stop quickly if it isn't a permutation matrix, and so can never become the identity matrix. We'll check if it's the identity matrix here. If it is, we'll set the return boolean variable equal to true and exit the loop. And we'll return the return variable here. We'll create a function to create a random permutation matrix. I've done this before in a previous video. I'll just go over it again here. This function creates a standard basis permutation matrix with 1s and 0s. We'll create an array with ordered elements so that the element in the array is equal to its index. Then we'll jumble up this list to create a random permutation. We'll set the dimensions of this matrix and the length of this permutation. This loop will insert zeros into every location of this matrix. It's faster to put the zeros in every position first. And this loop puts the 1s in according to the permutation that we've just created. So here's the program to construct a matrix with a tiny difference that stops it from being a permutation matrix. I've done this by adding a non-zero 1 element to a random position in this matrix. So we can use these functions to conjugate these newly created matrices with another invertible matrix, so that we'll have non-standard basis forms of these matrices. I've explained conjugation in earlier videos that I've made about matrices, like testing for nilpotent and projection matrices. This is the main loop where we'll test these functions. We'll firstly create the table of maximum values. Then we'll test it here for 1,000 non-standard basis permutation matrices. We'll test this function and it should always return true. Then if it returns false, we'll return an error and write out the values of these matrices. And we'll create a second loop to test it for non-permutation matrices, and it should always return false. I've ran a few results and I occasionally get an error. The top matrix is the matrix to be tested, and the bottom matrix is the matrix raised to a power. It looks like it was very close to the identity, but some numerical errors crept in. I got this a few times, once for every 1,000, so it looks like it works well in theory, but not always in practice. It probably needs to work with more accurate numbers, like the big number type, which can store a number to 64 significant figures, which would suit such a program. It probably needs some other tweaks as well, like for example, the matrix A has some fairly large numbers in it that are over 1,000. So maybe this matrix needs to be multiplied by a constant, so as to make all of its elements smaller. This might help. This is the function that checks whether C is the identity. This part circled in red determines the accuracy of this function, so it can accept matrices that are fairly inaccurately equal to the identity matrix, as being equal to the identity matrix. So I hope that you have found this video helpful and insightful. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments, and feel free to share this video. And thanks a lot for watching.